Now we need to learn some vocabulary. What is a monotonic sequence? A monotonic sequence. It's non-decreasing or it's non-increasing. So non-decreasing sounds like it would increase, but not necessarily, because it could also be equal. Right? So they're either they stay the same and grow, or they stay the same and they get smaller. So that's a monotonic sequence. And we're going to look at some of those. If a sequence is bounded and monotonic, then it converges. Okay? So looking at the graph of 1 over n, which was in the previous example, and again, the reason why I did not connect the dots is because these are not all real numbers. Remember, n is 1, 2, 3, 4, and so forth. So you can only have when n is 1, when n is 2, when n is 3. You cannot connect the dots. So, is this monotonic? Well, let's see. It's certainly non-increasing. Okay, so we're getting smaller and smaller and smaller. Is it bounded? What does bounded mean? Bounded means it's between values. So the highest this goes is 1. The lowest it goes is not quite 0. So it is bounded, it's monotonic, and therefore it converges. So let's look at this graph. It's just -1 to a power. So what are we going to get? We're going to get a -1, we're going to get a +1, -1, +1, -1, +1, -1, +1, forever. So the first question is the sequence bounded? And the answer is yes, because we are bounded between -1 and +1. The second question is A sub n monotonic? Okay, remember, monotonic means non-decreasing or non-increasing. Well, this is not, because this goes up and then this goes down. This goes up, this goes down. That does not fit the definition. So no. And if you look at this also does not converge. Let's look at this graph. Okay, so again, remember, these are your n values, 1, 2, 3, 4, 5. So you can see that it's definitely increasing. So that means it's non-decreasing. But how could we prove that this is monotonic? We can take the derivative. Okay, because we want to show that it is non-decreasing, which sounds like increasing, but non-decreasing. So this is what you have to do, and this is the part of the chapter you're not going to like. In order to take the derivative, we have to be very careful of our notation. We have to let a function with all real numbers equal to x squared over x plus 1. So we have a function associated with our sequence. But in order to take derivatives, again, we can't just do it over natural numbers. We have to have a continuous function. So I'm going to take the derivative using the quotient rule. So bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So simplifying this, we have 2x squared plus 2x minus x squared over that. And so that's going to be x squared plus 2x over x plus 1 squared. Now what does that tell us? We need to know, in order for it to be non-decreasing, our derivative needs to be positive, right? Because if it's always positive, then that means our function is increasing, which is close to non-decreasing. So how do we know that? How can we prove that? Well, first of all, we know the denominator is always positive. Doesn't matter what x is, put it in there, add 1, square it, you're going to get a positive. But what about that numerator? Is that always positive? Well, I don't think so. So if we set this equal to 0, like we did in Cal 1, and find our critical values, we get x is 0 and -2. If we look on a number line, then we can evaluate this numerator at those different values. So if I plug in -3 in here, I'm going to get negative. If I plug in -1, or do I get negative? Let's see, 9 minus 6. No, I get positive. I get positive 3. If I plug in -1, I'm going to get 1 minus 2, and I get negative. But if I plug in numbers bigger than 0, I'm going to get positive. And you're going, well, then it's not monotonic because the function, if its derivative is positive, negative, positive, that means the function is increasing, decreasing, increasing, and that would not fit our definition. But remember, our sequences, the domain is natural numbers, bigger than 0. So all we care about is this part. We don't care what happens there. We just need to know that when x is larger than 0, our derivative is positive, which means our function is increasing. So let's write all that down. Okay? So when x is greater than 0, our derivative is always positive. So therefore, we can say our sequence is monotonic because our associated function is increasing when x is greater than 0. So that's how we can prove something is monotonic, by taking the derivative, but you have to start out with a function in terms of x. Some very useful limits to know as we go through this chapter are listed here. We can go through, we've proven most of those when we did L'Hopital's rule, right? So just good things to know. The natural log of n over n equals 0, and that's just because the natural log of n does not grow as fast as n. Okay, if x is bigger than 0 here, and you're taking 1 over n, you're going to approach 1. Now, we actually proved this doing L'Hopital's rule and logarithmic differentiation. So depending on what x is, you're going to, if x is 1, you'd have this e. If it was 2, it'd be e squared. Very, very helpful. These pretty much are almost exactly the same thing, but one is in terms of x, one's in terms of n. Then we've got this one. We've got some number whose absolute value is less than 1. It's like a half, a third, a negative 1/5, taking the absolute value and raising it to powers. You're going to get smaller and smaller. And then this one. Look at that. We've got factorials. And that's again because factorials grow so much faster than exponents. So your denominator is going to be a factorial. So we have exponential function divided by factorials. These grow faster, so our limit is 0. So let's review what factorials are. Again, natural numbers. However, special case of 0 factorial that we define to be 1. So just to go back and practice what these mean, so you want to always start with the largest and go down. So this would be n plus 1 times n, okay, times n minus 1 times n minus 2 forever. Okay, what does this mean? It means n minus 1 times n minus 2 forever. Okay. So what could we do to reduce them? All the forevers would reduce out, reduce, 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 1. And so this would equal to 1 over n times n plus 1. Okay, just simplifying factorials. Again, you want to start out with the largest and go down. So really, n factorial writing like this. So think about 5 factorial is 5 times 4 times 3 times 2 times 1. It always descends. So we want to start with the largest. So we have 2n plus 1 times 2n. Goes forever, but I'm going to stop because that's exactly what I have in the denominator. And then I can reduce those and just be left with 2n plus 1. Those are going to come in handy. All right, so do the sequences converge or diverge? If it converges, find its limit. So looking at number 8, how do we do that? Well, let's look at this and this. And look at where that n is. So if I just look at cosine of n pi. Now remember n, 1, 2, 3, 4. So we're looking at the cosine of 1 pi, 2 pi, 3 pi, 4 pi. What does the cosine equal to at pi? At negative 1. 2 pi, positive 1. 3 pi, negative 1. So what does this do? It oscillates between negative 1 and positive 1. Multiplied by n pi. Well, even though we have plus or minus, what is this doing as n gets really large, multiplied by pi, which is like 3.14, that's going to approach infinity. So we can say the limit as n approaches infinity of a sub n, we can say it diverges. The limit does not exist. What about this one? The limit as as n approaches infinity. Well, this one, what happens to this fraction as n gets really large? It goes to 0. What about here? It goes to 0. So really, I have 2 times 3, which is 6. So we would say it converges to 6. Yes, that's all there is to it. Okay, so we have some factorials. So before you do anything, simplify it. Which one's bigger? N is bigger than n minus 2. So I'm going to start with n minus 1, n minus 2, going to stop, going to reduce. So really, a sub n is 1 over n times n minus 1. So I want the limit as n approaches infinity of that sequence. I know you know this, as this gets really huge, this approaches 0. So therefore, it converges to 0. What about this one? Well, you might want to look at this as 5/3 to the power of n. Now 5/3, that's approximately 1.67. If you take a number larger than 1 and keep raising it to powers, what's going to happen? It's going to diverge. So the limit as n approaches infinity of 5/3 to the nth power diverges. The limit does not exist. Number 12. What the heck is this? We have e to the n over pi to the n. Well, just like number 11, this can be written as e over pi to the n. Now, e and pi are just numbers, just like 5 and 3 were. But 5 over 3, that ratio was bigger than 1. But what about e over pi? So e is about what? 2.718. Pi is about 3.14. Again, this is an approximation. What about that? That's less than 1. Okay, so when you have something smaller than 1 being raised to a power, that limit as n approaches infinity is going to equal to 0. So we would say it converges. That goes back to this right here. As long as the absolute value of x is less than 1 being raised to a power, you get 0. And of course, if it's greater than 1, it's going to diverge. So in conclusion, you really need to understand what a sequence is. You need to understand the notation. You need to know how to associate a function with real values to a given sequence so we can use what we know about limits. If you have an oscillating function because of negatives, it's nice to know that you can take the absolute value. If the limit of the absolute value equals to 0, then we can say the limit of the given sequence is 0. And you also need to be aware of what does monotonic mean. And again, some really good limits to review.